Let's take a look at this example where we are asked to evaluate the double integral over d of x plus y times e to the power of x minus 2y dA, where d is the parallelogram with vertices 1, 0, 3, 1, 5, -1, and 3, -2. It isn't strictly necessary, but let's go ahead and produce kind of a rough sketch of what d looks like. Let's see if that's enough space for us. If we do about 1, 2, 1, 2, 1, 2, 3, 4, 5. Yeah, I think that'll work. So we have x and y. We have the points 1, 0, 3, 1, 5, -1, and 3, -2. So we have this parallelogram here, and this one is not as bad as it could be because these 2 points happen to lie in the same vertical line. So if we wanted to do this directly, we could split this up into just 2 integrals, one of them bounded above and below by these lines, the other one bounded above and below by these lines, and then grind through all of that. Still a little bit of a pain though. And if these were offset slightly, then we would need at least 3 regions, and that would not be particularly fun. So let's look at finding a transformation to make this region much easier to deal with. Before we do anything with these problems, we do need a transformation. I mentioned in my notes there are the 3 main things to look at in terms of the bounds, translating the integrand, and finding the scaling factor, but all of those follow from assuming that we have a change of variables that we're going to be using. So for example, when you're doing a problem with polar, you know what transformation you're using. You have that, x equals r cosine theta, y equals r sine theta. Those are the equations describing the polar transformation, and everything follows from that. So here we need a transformation. Most of the exercises you're given will supply a transformation for you, so you can just sort of dive right in and start working with this. Some of them do not. So I wanted to go through some of the techniques we might use. In this particular case, where we have a parallelogram with given vertices, usually what I find to be the easiest way to do this is to begin by finding equations to describe the boundary lines, right? So looking at some of these, trying to find what's easiest to work with. This line down here looks like it has a slope of -1, so that's convenient. And projecting backward, it would have a y-intercept of 1, so it looks like we have the line y equals 1 minus x for that side. The opposite side, if this is a parallelogram, this should have a similar slope, again -1. If we go right 2, it goes down 2, so that works. If we go left 3, it should come up 3. So from 1, we have 2, 3, 4. So it looks like we have 4 minus x. I'm just kind of eyeballing these right now. We'll check them in a moment. This side here, now we have a slope of 1/2. So this is 1/2 x minus, using that slope of 1/2, going left a unit, that'll come down 1. So we have minus 1/2. -1/2 would be our y-intercept there. And this side over here, again, has a slope of 1/2. And we're at 3 here, so if we come left 3, we'll come down 3/2, so that looks like a total of -7/2. Let's take a moment to make sure that this is working. We can do this by trying our vertices, right? So the point 1, 0, for instance, should satisfy both of these equations. And if we plug in 1 for x here, we get 0 for y. 1 for x there, we get 0 for y. That looks good. The point 5, -1 should satisfy both of these equations. If we plug in 5 here, we get -1. If we plug in 5 there, 5 halves minus 7 halves is -1, so that works. You could check the other two as well if you want. we can confirm that these equations describe those corners. Now, this looks like sort of a mess. How does this help us find a substitution? What I find usually to be easiest is to try rearranging the equations to get constants on one side and the variables on the other. So looking at this equation down here, for instance, y equals 1 minus x. If we add the x to the other side, that becomes the equation x plus y equals 1. And looking at the opposite side, y equals 4 minus x. Again, if we add the x to the other side, we have x plus y equals 4. So you see how we end up with the same structure here. Looking at these other two, we probably want to multiply through by 2, and then do a little bit of manipulation. So if we add that over, and again multiplying by 2, it looks like we'll have an x minus 2y equals 1. And this one down here appears like it'll give us an x minus 2y equals 7. So this structure here, seeing these repeated patterns, this suggests that we let u equal x plus y, and let v, there's nothing special about u and v, you can pick whatever variables you want, let v equal x minus 2y. You see why? Because we have, if we do this substitution, these equations become u equals 1, u equals 4, v equals 1, and v equals 7. And those are much nicer. If we were to plot those in like a UV plane, let me just drop out something very quickly here. Actually, that is not the right proportions. I think we had, what, v going from 1 to 7, u going from 1 to 4. This is not really to scale, but yeah, use your imagination. So we would get some sort of a region like this in the UV plane, as opposed to this parallelogram in the XY plane. I'm sure you can see that this is a much easier domain to integrate over. So what we see here is that this system of this transformation here, the system of equations, defining uv as a function of x and y, if we take each xy point in here, that should translate to a corresponding point over here. Okay? So for example, if you take the point 1, 0, you have 1 plus 0 equals 1, and 1 minus 0 equals 1, so you'd get the uv point 1, 1. And that is this right here, right? If you take the point, what was the next one? 3, 1. 3 plus 1 is 4, and 3 minus 2 is 1, so you would get the uv point 4, 1, and 4, 1 is right here, and so on. Your other two vertices would give you 4, 7, and 1, 7. So that is two different ways to get the bounds on u and v. We now see what those bounds are. That's one of the three things that we need, are the bounds on our new variables. You can get them, sometimes you can get them from the equations that describe the region and knowing what the substitutions are. Other times you might want to take, for instance, boundary points, the corners, and run those corners through the substitution to find your UV pairs. Or occasionally, if you are given equations, you might want to put those equations through the transformations and find out what you get in terms of u and v. There are plenty of ways of doing that. There's lots of different kinds of information you might be given. You just have to kind of algebraically work with what you have to figure out what you need to know. So that is one of the things we'll need. Even if we were given a transformation like this, in order to continue, so we have u and v in terms of x and y. Now we need to find x and y in terms of u and v. And even if we were given x and y in terms of u and v, we would then still have to do the algebra to get u and v in terms of x and y in order to find the bounds, probably. So whichever order you find the transformation in first, you will usually also have to find the inverse transformation. And that's really just solving a system, right? So, looking at this thing, for instance, we see that, okay, if we take u minus v, x minus x would cancel out, y minus negative 2y is 3y, and that tells us that y is equal to u minus v over 3. I just sort of eliminated the x's. And similarly, if I want to eliminate the y's, I could take 2u plus v. We have 2u plus v, that's a 2x plus x gives us 3x. And we have 2y plus negative 2y, those cancel. And now we see that x, solving for it, looks like 2u plus v divided by 3. So here is one expression of our transformation, and this is the inverse transformation. These two pairs of equations together give us everything we need to know about moving from one to the other. And like I said, whichever one you find first or are given, you're probably going to need to switch to the other one to find the other thing. So if you were given this transformation, you would still need to find, okay, what are u and v, so that you can find out what the bounds on u and v are. Knowing this transformation here, what x and y are in terms of u and v, that allows us to compute the scaling factor through the Jacobian, or Jacobian, I guess most English speakers say, but it was named after Jacobi, so that feels weird to me. I don't know, call it whatever you want. But the Jacobian, or Jacobian, is usually designated by this fancy symbol, where we use the same symbol as partial derivatives, but it's not exactly a partial derivative because we have these points in here. It's kind of weird, but it's just regardless of the meaning of the symbol there, this represents the determinant of a matrix built of all of the possible partial derivatives. So the symbol sort of reminds us how to build these up. It's the partials of x and y, each with respect to u and v. So this would be the partial of x by u, the partial of x by v, the partial of y by u, and the partial of y by v. Now, if you forget whether it goes rows or columns first, it doesn't really matter, because if you swap this diagonal here, you still get the same determinant. There's a property from linear algebra that a matrix and its transpose have the same determinant. Or if you switch the order of things and you change which columns are which or which rows are which, that'll just sort of, that might give you a negative of the determinant, but in the end we'll be taking an absolute value anyway, so the negative won't matter. But let's look at what we have here. The partial of x by u, looking at our expression here, x is defined as a function of u and v. If we hold v constant and take that partial derivative, we have 2/3 as the partial of x by u. Partial of x by v looks like 1/3. The partial of y by u is 1/3, and the partial of y by v is negative 1/3. Oh. There we go. So now we have this 2 by 2 determinant. Evaluating that, we have 2/3 times negative 1/3 is negative 2/9, minus the back diagonal is 1/9. That is negative 3/9, or negative 1/3. That is the value of the Jacobian. It is a scaling factor. So what this tells us is that the dA, or dx dy, actually we weren't given dx dy, we were just given dA, so let's write it this way. So dA is equal to, we want to take the absolute value of the Jacobian. If it comes out negative, we make that positive, so we get 1/3 du dv. So this dA that would be our dx dy is 1/3 du dv. That's a scaling factor. In fact, if we come back here and look at this, so if you look at this rectangle, you see it's 3 by 6. That has a total area of 18. And if you work out the area of this parallelogram, I encourage you to check on that, you'll find that that has an area of only 6. So what we see here is that to get du dv and translate it to dx dy, we need that 1/3 scaling factor to account for the change in areas. The negative happened because this sort of flips over. So I mentioned when I was evaluating a couple of points, we started with this corner, 1, 0, and then I went up to 3, 1 to evaluate that. So I was kind of moving in a clockwise direction. But you see that when those map to 1, 1 and 4, 1, that's moving in a counterclockwise direction. So if you were to take this parallelogram and we can shift it and scale it and apply shears to it to skew it in various ways, and turn it into this rectangle, at some point you're going to have to actually flip it over. There's going to be reflection there, and that gives us a negative. That isn't necessarily the case. If we had made a different choice of variable substitutions, we could have ended up with one that did not flip and gotten a Jacobian that was positive. We don't care whether it flips over or not. All we care about here is that scaling factor on the area. So we get that 1/3 coming into there. And that actually tells us everything we need to know to compute the integral. I've got a lot of stuff going on here. So let's bring that a little bit closer. I have another version of this. So that means that the original integral of x plus y times e to the x minus 2y dA would be equal to the iterated integral. Now, we have x plus y. We need to figure out what to replace that with. If we are unfortunate, we might need to just do that directly. Okay, x is this thing, y is that thing. Let's add them together and simplify. But if you do that and you take a close look at what's happening here, these fractions would combine, the v's would cancel. You get 3u over 3, which is just u. And in fact, we know that u is equal to x plus y. So this x plus y is just u. And similarly, you could plug in what you know about x and y, but x minus 2y is v. They were very kind to us, the authors of this problem here, which I did not write. I'm very bad at making up examples. They were very kind to us, and they gave us an integrand that also simplifies under the appropriate transformation that simplifies the domain. That won't always happen, but here at least it did. dA, we found that we have the scaling factor of 1/3, and it doesn't matter whether we write du dv or dv du, since we have constants here. We just have to be careful to put the right things on the right things. U goes from 1 to 4, v goes from 1 to 7. So u goes from 1 to 4, v goes from 1 to 7. And there we go. There's our new integral setup. And it is reasonably straightforward to finish evaluating that, right? We can pull the 1/3 out front. We see that this is separable. So we have the integral from 1 to 4 of u du times the integral from 1 to 7 of e to the v dv. So we have 1/3 times 1/2 u squared from 1 to 4 times e to the v from 1 to 7. Combining those, that is 1/6 times 16 minus 1 times e to the 7th minus e to the 1st. And that is, we have 15 over 6, which is 5/2 times e to the 7th minus e. Now, is that less work than setting this up as two integrals over the parallelogram? I don't know. I haven't actually tried that. Maybe that would be easier. I suppose it depends on how comfortable you are with these transformations. But like I said, this is a relatively simple arrangement. It could have been a little bit worse if these vertices did not line up on the same vertical line. We would have 3 integrals to work out separately, I kind of like this. Right? Once we do that transformation, as it happens, everything cleans up very nicely. It becomes a relatively simple integral to work through. So yeah, that's the idea here when we do these transformations. Again, just like when you're converting to polar, or if we were in triple integrals and you did something in spherical or cylindrical, you basically have, once you know the transformation, you need three things. You need to know how to describe the integral in the new space, figure out what the bounds are. You need to be able to translate the integrand to the new variables, which, if you're fortunate, there will be things you can group and simplify nicely. If you're slightly less fortunate, well, you can just use the appropriate version of the transformation, plug in what you have for the variables, and simplify as much as you can. Right? Worst case scenario, it's just algebraic substitution. And the big thing to not forget is we always need to find that scaling factor. Right? And that's not new. Remember, hopefully you've read the notes in the textbook, so you recall that in the when we use the polar transformation and we compute the Jacobian, we get r, that r dr d theta. That r is the scaling factor that we compute by taking, the determinant of all the partials that are involved. If you do that with cylindrical, you also get r. If you do it with spherical, out pops the rho squared sine phi. Right? I recommend working through those yourself. They are worked out in the textbook, but try them on your own. Just doing that once in your life, I feel is a useful exercise to kind of see where those come from and solidify and kind of internalize that, okay, yeah, this isn't just something I'm accepting on faith. I see, like, this is what we compute as finding these, taking these partials, working out that scaling factor. In the case of a linear transformation, like what we have here, you'll note that these equations, these functions are all linear. That's why the Jacobian came out to be constant, because it doesn't matter where you are in the region, the scaling factor is going to be the same. When you have a nonlinear transformation, like with polar, well, then it matters, right? If you think about a polar situation, just as an aside to illustrate here, if you think about polar and you have something like, something like this, let's say, 1 to 2, 1 to 2, and you have this region in here. This is what we called a polar rectangle. And the reason for that is that if you plot this in the theta r plane, you might have done a little bit of this with theta and r in Calc 2, possibly. If you come out to, like, what do we need there? Pi over 2. Here's our origin. Then this region becomes this region, right? And the thing is, this part here, if you think about the stretch of, the whole little narrow strip of things down near 1, that corresponds to this arc right here. But if you think about the strip that's near 2, that little strip at the top corresponds to that arc there. And hopefully you can see that this outer arc is longer, right? If you look at something that's very close to 0 in R, this whole stretch right here, that long strip, gets mapped to this tiny little bit right here, down near the origin, right? Whereas if you take something out at like 10, with a radius of 10, now you have this gigantic arc in the xy plane. So the polar transformation is nonlinear. And the scaling factor of areas, if you take a tiny little piece of area and you find out what little piece of area does it correspond to over here, well, the scaling factor is going to depend on how far you are in the r direction. The greater r is, the greater the scaling factor. And it's directly proportional to r. And that's basically why, physically, when you compute the Jacobian, you get that scaling factor of r along with the dr and d theta for your differential area. This thing here is because of that scaled distance. So again, stepping back to this thing we had here, in this case we had a linear transformation, so we just got a constant. With a nonlinear transformation, you'll get something else, and then have to deal with how that interacts with your integrand. But again, this is just a generalization of those changes of variables that you've been doing in earlier sections. Polar, cylindrical, spherical, those were special cases, common situations that show up a lot. And now here's the general rule that encompasses all of those.